Hello again, and welcome to Advanced Physics for High School students. This is Lesson 24, and it is entitled Coulombs Law.
It has to do with quantifying the electrical forces electrostatic objects exert on each other. Let me remind you back from lesson 21, one of the basic facts we enunciated about electrical forces is that there are two types of electrical objects, which we can call positive and negative, and they can exert forces on each other. We say that like forces repel and unlike forces attract. And we said what causes an object to be electrostatically charged is that there's an imbalance of positive charge, which is attributed to protons, and negative charge, which is attributed to electrons. We said that protons and electrons have the same magnitude of charge but opposite signs, and that when there's an imbalance, it's as a result of a shifting of electrons away from one object to another object. And these electrostatic forces are ones that can push the objects around. We said back in lesson 21 that we would save the magnitudes of the forces until a later lesson. And now we have come to that later lesson. What we want to do now is to quantify, to say how much force do these charged objects feel, and numerically is instated in a law that's called Coulombs Law. Let's suppose that we have two objects which have been electrically charged. We'll call one of the excess amounts of charge Q1 for quantity of excess charge on object 1, and the other one Q2, which is the quantity of excess charge on object 2. And we'll suppose that these two objects are separated by a distance r. Coulomb's law says the force that these charges feel is given by an equation. That equation looks something like the equation for the gravitational force. Here is what the equation says. The electrostatic force is equal to some constant K. It's an electrostatic constant that's going to be the same for all the problems that you solve, times the quantity of excess charge on object 1 times the quantity of excess charge on object 2 divided by the square of the distance between them. This electrostatic constant K has a numerical value 9.0 times 10 to the 9th Newton meters squared per Coulomb squared. You'll notice that this formula bears resemblance to the gravitational formula, except the constants are different. The thing that appears in the numerator are quantity of excess charges in this case, whereas in the gravitational law, it's the amount of mass of the objects. There's also another important difference, and that is the electrostatic force might be positive or it might be negative depending on what the charges involved are. In other words, the forces might be repulsive forces if the charges are like charges, but they might be attractive forces if they are unlike charges. And so the direction of the force depends on what the relative signs of the charges are. That can make Coulomb's law a bit confusing, especially when there are several charges interacting. So I prefer to write Coulomb's law in a different way. This looks a little more confusing. In my mind, it's a bit clearer because it makes some things explicit. Here I've written absolute value signs around the electrostatic force between particles I and J. I means maybe number 1, J means number 2. It could be any pair of particles because you may have a collection of 3 or 4 or 5 or Avogadro's number of particles, and each of them might be exerting electrostatic forces on the other one. The magnitude of that electrostatic force between the ith and the jth particle is equal to the electrostatic constant times the magnitude of charge I times the magnitude of charge J divided by the square of the distance between those two charges. F-E-I-J means the force on particle I due to particle J. And this may remind you of Newton's third law where we talked about the force on object X due to object Y. And my suggestion is it's best to work with magnitudes of forces and to draw good diagrams showing the directions that the forces exert depending on what those signs of the charges are. There are going to be some numerical examples that we'll do below that will illustrate this point. For the moment, let's just suppose that I have a collection, say, of 5 charges. These charges all are going to exert attractive or repulsive forces on all the other charges as a result of where they're located and the fact that they have excess charge. I'm going to have forces that are exerted on these charges that are going to be very complicated if it goes to calculating what those forces are. I'm going to number these charges. You can see in this diagram there are going to be forces on all of these charges, and those forces can be quite complex. So let's say that I were just focusing on the third charge, and I want to figure out what is the force that's exerted on charge 3 due to the other 4 charges. Schematically, I'll sketch it this way. There's a force on charge 3 due to charge 1, that's attractive. There's a force on charge 3 due to charge 2, that's also attractive. There's a force on charge 3 due to charge 4, that's also attractive. And there's a force on charge 3 due to charge 5, that's repulsive. Now, suppose I gave you charge amounts for Q1, Q2, Q3, Q4, and Q5. And suppose I gave you distances and angles between each of these charges. You can see that this becomes a very complicated vector problem, trying to figure out the force on 3 due to the other charges. That's just the force that's on one of the charges. All of the charges are feeling forces. 1 feels forces due to 2, 3, 4, and 5. 2 feels forces due to 1, 3, 4, and 5. 4 feels forces due to 1, 2, 3, and 5. And 5 feels forces due to 1, 2, 3, and 4. That's a very complicated problem. And you probably won't get something as complicated as that on the exam. In principle, we can use Coulomb's law to figure out what the vector forces are. Then if the charges are free to move and they begin to change spaces, then you can see that the directions change, the distances change, and the calculations get very complicated as the charges move. Generally, the way these problems are going to be pitched to you is that there's a fixed instant in time at which you want to calculate the force on one of the charges due to all the other charges. And generally, you're going to be asked to figure out what is the magnitude and direction of the net force on that one charge due to the other charges. We've got a Coulombs Law problem in which we're making a calculation of the force, and then we have a vector problem in which we're making a calculation of the angle that that force makes. Before we get to some numerical examples, I want to make some comments about this electrostatic constant, K. There's another common way that this electrostatic constant is written. It will sometimes be written as 1 over 4 pi epsilon naught. So another way you're going to see Coulomb's law written will be something like this. And the 1 over 4 pi epsilon naught means the same thing as the K, the electrostatic constant. So what is this 1 over 4 pi epsilon naught? It comes from calculus and some geometry involved something called Gauss's law. That is an advanced physics topic that we're not going to get into in this course. Epsilon naught is known as the permittivity of the vacuum. It's a fundamental constant. It turns out matter tends to become polarized when it's placed close to charged objects. We talked about the polarizing of materials, maybe like a pith ball, or the polarizing of a conducting sphere when it's placed close to a wand that has excess charge on it. Permittivity is a measure of how the electric field affects this material. Basically, epsilon naught is a number that represents how easy it is for an electric field to pass through a vacuum where there's no material at all. It has a numerical value, 8.85 times 10 to the minus 12 farads per meter. Farad is a unit of capacitance. We'll talk about capacitors in a future lesson. Just like newtons are a combination of kilograms and meters and seconds squared, farads are combinations of units as well. Epsilon naught is equal to 8.85 times 10 to the minus 12 coulombs squared per newton meter squared. If you were to take the ratio, the fraction 1 over 4 pi epsilon naught, well, you put it in your calculator and see what you get. 1 over 4 pi epsilon naught is going to be equal to 1 over 4 pi times 8.85 times 10 to the minus 12 coulombs squared per newton meter squared. So now put that in your calculator and smoke it. What I get in my calculator is 8.9918 times 10 to the ninth. And if you round that to 2 sig figs, you get 9 times 10 to the ninth newton meters squared per coulomb squared, which is what we've said is the electrostatic constant K. Now let's go and work some numerical problems. Point charge A is composed of 9,250 electrons and is 66 centimeters from point charge B, composed of 61,500 electrons. What is the magnitude and the direction of the electrostatic force on charge A? Well, first of all, let's recognize that when we say a point charge, all of the excess charge is concentrated at a point. That's an idealization, but that's one that you're going to make in all of these problems that you do. Let's also recognize that when we say it's composed of 9,250 electrons, we mean that it has that many extra electrons more than it has protons. Since electrons are elementary charge, and the elementary charge is 1.6 times 10 to the minus 19 coulombs, then we can figure out what is the amount of excess charge on object A. And likewise, we can do that for charge B. We'll need to know those numbers in order to put them into Coulomb's law. Let's sketch a diagram. I'm going to need to work in MKS units, so I'm going to convert that 66 centimeters to 0.66 meters. If there are electrons on A and B, then these two spheres are negatively charged. Because they are like charges, they're going to exert repulsive forces on each other. So I'll indicate that in my diagram. So whatever number I come up with from Coulomb's law, charge A is going to be pushed in my diagram to the left by charge B. And likewise, charge B is going to feel a force to the right exerted on it by charge A. We're interested in the magnitude and the direction of the electrostatic force on charge A. Charge A is going to be pushed to the left. Now we need to figure out what the force is. But first I got to figure how much excess charge there is on each of the objects. The excess amount of charge on charge A is equal to 9250 times the charge on one electron, 1.6 times 10 to the minus 19 coulombs. And I get a number. The amount of excess charge on object A is 1.48 times 10 to the minus 15 coulombs. Coulombs is going to be the measure of MKS unit of electric charge. Let's do the same thing for charge B. Since charge B has 61,500 electrons, I multiply that times the charge on one electron and I come up with some number. An excess charge of 9.84 times 10 to the minus 15 coulombs. Both of those charges are negative, but I have not put in a negative sign here. I'm going to let the diagram tell me the direction of the forces. I'm going to use Coulomb's law to calculate the magnitude of the electric force. So now I'm going to put these numbers into Coulomb's law. And I know all those numbers, so I'm going to put them in. I'm going to put them into my calculator and come up with some result. And my result is that the force on A due to B is equal to 3.01 times 10 to the minus 19 newtons. And the direction is that A gets pushed to the left in this diagram. Frequently, you'll see that there will be a coordinate system that's given to you, and you'll be asked to say what is the direction of the force on this particular charge in that coordinate system. So just briefly, let me sketch a coordinate system here. In this coordinate system, positive x is horizontal, positive y is vertical, and we see that the force on A due to B is in the negative x direction. Frequently, you'll have to express the direction in terms of a given coordinate system. So that's it for this particular problem.